And welcome back to SciByte, everybody, where we explore the mysteries of the infinite universe and all of the tools and technology that science is using to get to the bottom of one and every one of them. My name is Jeremy, and joining me on the Skype line, as every week, is Heather.
Hi, guys. Today we're going to take a look at lightning, how it works, the facts about it, and to maybe take a look at some of the myths or rumors.
It's probably going to be a shocking experience. Now, why are we going to talk about this, though, Heather? I mean, doesn't everybody out there know everything there is to know about lightning? It's such a kind of a mundane thing, isn't it?
No, not really. Science doesn't know exactly what guides the path of lightning, why it strikes in one place or another. We don't know all the answers to lightning.
Well, let's face it, it's kind of hard to put lightning in a lab, at least to the same scale as what occurs in nature. You can't exactly wrap a lab around an entire thunderstorm.
No, we can shoot a rocket with a little spool of wire behind it into a thunder cloud, to kind of induce lightning to follow that spool down and be able to study a little bit that way, but it's still not quite the same and obviously won't work necessarily every time, but...
And also that little spool that they shoot up there is basically an artificial conduit for the lightning to follow. That's really interesting to know if you knew how lightning was formed, which we'll get to in a little bit here. But that is an actual technical term for when they shoot a rocket into the clouds. They call it rocket lightning.
Rocket lightning. Rocket-induced lightning.
It's a real thing.
Yeah.
Are there other types of lightning then, other than just the basic bolts that we're used to knowing about?
Well, I mean, there's, cloud and cloud lightning, cloud to ground, ground to cloud. We're actually two different things, how they originate. Bead lightning, ribbon lightning, all sorts of different heat lightning, rocket-induced, which we spoke about, positive lightning, even lightning that does not require precipitation, like in dust storms or volcanoes, where the dust itself is causing the static charge.
Wow. But I think for today's show, correct me if I'm wrong, we're going to focus primarily on what the basic type of lightning, cloud to ground. What probably everybody knows about, the big, beautiful bolts of lightning that go on during some of the massive thunderstorms that you've been experiencing firsthand over the last couple of weeks there where you live. So tell me, since that's the type of lightning that we're going to be focusing on in this episode, I think it's good up front to go ahead and show people, to tell people exactly what's going on in this crazy phenomenon that causes bolts of light to shoot from the sky down to hit things on the planet that we live on.
So clouds themselves form when the air reaches a dew point, which most people have heard about. It's when the air has reached a temperature that it can no longer hold more water without it starting to ball up and form. So you start having little balls of water or clouds or fog or things like that.
Basically either little tiny droplets of water or crystals of ice, depending on the temperature.
Depending on the height, the atmosphere, or the temperature, that is correct.
Right.
And so when you have these big clouds starting to form, these cumulonimbus clouds, the big...
That's a mouthful, isn't it? What is it? Cumulonimbus?
Yes. Cumulonimbus.
That's the type of cloud that's most frequently associated with lightning?
Yes, it's those anvil-shaped clouds that you sometimes hear about.
Right, the really tall ones with kind of the flat bottom that...
Yeah. So when you have those, then you'll start having warmer air from the bottom of the cloud start to rise. The cooler air, ice crystals in the top of the cloud start to fall. So you've got rising and falling objects, ice crystals in water. And when that happens, when those items strike each other, these two neutrally charged items, there's a chance that an electron can sort of jump ship from one to another. So then you have one negatively charged and one positively charged.
So we're talking at a molecular scale here of what actually starts the buildup of the electrical charge that will eventually become lightning. It's actually caused by two particles of water or whatever. Actually, it's probably good to mention that lightning can form anytime there's a region of our atmosphere that's molecularly crowded. You did mention volcanic ash, dust storms. Tanner in the chat room actually also mentioned that thunderstorms can form over forest fires just from the smoke rising from
the ash itself from a forest fire. Anytime there's these small molecular items that are hitting each other, they can exchange electrons, and the same function can happen where you have negatively charged stuff and positively charged stuff. Now in a thunderstorm, you'll have in the cloud, you'll have the bottom is sort of pooling with negatively charged material, and the top of the cloud is with positively charged material. Now, sometimes you can have that cloud lightning where it strikes with each other.
Right.
But for cloud-to-ground lightning, which we're interested in, that negatively charged pool sort of, opposites attract. So it sort of pulls the positive charges in the ground to sort of pool underneath it. So now we
Wow.
have a negative pool in the cloud and a positive pool on the ground.
So even at the distance that we're talking, like the miles that can exist between the ground and the cloud, where these negative ions are pooling up, even then they can already start to attract each other?
Yes. There's enough of a charge buildup that the ground will realize that there's a negative charge above it, and it'll start to pool the positive charge in the ground. So now you have this negative charged pool in the cloud that starts realizing that there's something in the ground that it wants to go hang out with. So you'll have this trickle of electricity that start coming down from the cloud. It'll travel maybe, 300 or so feet and then stop, kind of pool up a little and then shoot off in a different direction, which is why lightning is never straight. It's all zigzaggy because it'll travel for about 300 or so feet, stop, pool, travel again in a different direction.
And again, this is the negatively charged particles coming down from the clouds, trying to reach the ground. And that's so this is creating what is called a leader, right? Am I getting the terminology correct?
That is correct.
And
so now this step leader gets within about 30 to 300 feet of the ground. And then the ground starts to notice that there's something interesting above it. So it will shoot off what they call streamers. And it's these positively charged little bits that sort of reach up. You might hear them before a lightning strike. You'll hear a crackle in the air. That's a streamer actually reaching up a potential lightning bolt.
I was kind of wondered what those crackling was. So that's actually, in a way, it's a leader. It's
A streamer.
It's a form of lightning coming up from the ground, and it's charging up in a positive stream trying to reach the clouds.
It's trying to reach that leader coming down. So it's sort of an almost lightning bolt. So you're hearing something that was close enough. You were almost close to lightning.
And we actually have a really awesome picture in our show notes that these streamers can, they can come up all over the ground where when there's a lightning bolt getting ready to form, when those negative ions start shooting down from the clouds, there can be whole fields of streamers starting. And correct me if I'm wrong, but that's one of the reasons that like your hair can start to stand on end when a lightning bolt's about to happen, and other cool stuff like that. Yeah,
and it's also why you don't always hit the highest target, because there's multiple streamers and it's sort of random as far as we can tell now as to why it chooses to hook up to one. So now we've got this positive streamer, negative streamer, and like I said, they can hook up, and that when they touch each other and hook up, that creates a conduit. So now they have hooked up and you have that return stroke, that's when we see the lightning. That's the flash that we see.
That's what you actually see, is not until those... Now, again, though, this all happens in the blink of an eye. Really.
Oh, yes.
I mean, those negative ions trying to reach to the ground and the crackling starting to start on the ground, it can happen less than half a second.
Oh, yes.
From the very beginning of when this starts to occur.
It takes much, much, much longer to explain than for it to actually happen.
Right. But it's all great because it makes those really pretty flashes that are completely non-dangerous, right? No, actually, we're gonna get in here a little bit about. I mean, there is a phenomenal amount of energy released. When that finally occurs, you guys will not believe what is actually happening on our planet. Nature is freaking wacky. When I started looking at some of the figures here about the amount of energy and heat and the speed that lightning occurs, this is some fascinating crap. I wish that we had better means to study some of this because it's incredible. Let's start with the amount of energy that can be discharged by a single lightning bolt.
Now, the voltage or power for any given lightning bolt is sort of proportional to the length of it. So, and as we knew, lightning zigzags around, so they're not all the same length. So you kind of have to talk about your average lightning bolt.
Sure.
And the average lightning bolt has about almost 4 times the largest man-made voltage.
It's that much more than we've ever created by hand. How much have we managed to, as humans, create a man-made bolt of lightning, basically, the voltage all at one place?
The largest man-made voltage is 25.5 million volts, which means the average lightning bolt is 100 million volts.
What does that translate to in terms of wattage? Like, how...
Wattage is power.
Right.
It means it's 1 trillion watts.
And how many gigawatts is that we're talking about there?
That is 826 times the power required to send a DeLorean traveling at 88 miles an hour from 1955 to 85.
I'm glad we got that science out in the open.
Yes.
It's good to know exactly how much. So
how many trips on the DeLorean can you take with one bolt of lightning?
800 and something.
826.
Okay, so that's fun. We can talk about sci-fi a little bit on SciByte, but really, I mean, there are real comparisons here to be drawn, right?
Oh, yes. 15 average bolts of lightning is about the average total power that the entire human world used in 2004.
Only 15 bolts of lightning could...
15 bolts of lightning, what the whole human world used in 2004.
That's crazy.
Yeah. And about 44 bolts of lightning, that's the average total heat flux of the Earth's interior.
Nothing big. It's just the interior of the planet.
And all of this is happening in about 30 millionths of a second.
All that entire process of the streamers forming.
All that, the streamers, the bolts, all the power, everything happens in 30 millionths of a second.
That is phenomenal. And
yes.
Lightning is awesome besides being pretty. How many? I'm just curious because we're talking about if 15 bolts could power the planet, 44 bolts is the same as the internal. How many times does lightning actually strike the planet, like worldwide?
On average, the world gets about 45 strikes every second.
So once a second, we generate enough power that is compared to the interior of the planet's. Okay. Lightning is not to be taken for granted. Okay, so we've talked a little bit about how phenomenal this is on our planet, but I don't know if you guys are aware, but there is lightning on other planets.
Venus and Saturn and Jupiter.
Right. In fact, right now, I think as we're recording this, there's a big lightning storm on Saturn being observed.
Yep, and the lightning bolts on Jupiter and Saturn are about 1,000 times more powerful than the ones here on Earth.
Gee, a single
bolt versus a single bolt, about 1,000 times stronger.
That's unrealistic.
Yeah.
Not literally, because it is real.
It's very real. But
now, okay, so we've talked a little bit about the incredibly massive raw amounts of energy that's released by this, but what does that translate to? I mean, everybody knows that it's hot. I mean, lightning can start fires with a single strike. It's got to be enough heat energy there, right?
Oh, yeah. It heats the air immediately surrounding it to about 3.5 times the surface of the sun, but the lightning itself can get over 5 times the temperature of the surface of the sun.
Oh, but we were sharing anecdotes before the show, and I guess that kind of explains, we've both had personal history of seeing trees explode when hit by lightning, because it's so hot.
The lightning heats up the sap inside the tree.
It evaporates it.
Evaporates it, and just
and
shoots
the tree
off
becomes
bits of tree everywhere.
A tree bomb.
Yes, it's a tree bomb.
You can see
bits of tree in the yard.
Yeah.
You have to try to pull out, and you can't. And then you're grateful you weren't standing there.
And the speed at which this all occurs. You said just earlier that all of this occurs in 30 millionths of a second.
Yep.
But how fast does that mean that lightning actually travels? I mean, there's some misconceptions out there that lightning is some sort of manifestation of light itself.
Yeah.
And
but it's not.
Quite
it's not
true.
actually traveling at the speed of light.
Right.
We talked about the leader coming down. And that is traveling at about 136,000 miles per hour, which could mean it could travel around the equator of the Earth in about 11 minutes.
Well, that's not phenomenally fast, but again...
But the return stroke that's the lightning, that could travel around the equator of the Earth in about 1.4 seconds.
That's much faster.
Much
and again,
faster.
It's the return stroke that you actually see.
This pooling,
that pooling of negative ions that snakes its way down to the ground. Although that happens extremely quickly, that's not what you see when lightning is happening.
No,
you're seeing
and it's not what's phenomenally even. It's just so phenomenally fast.
Right. And it is because of those incredible speeds at which this happens that's why we get thunder.
You're ionizing the air and you're heating all this air up in such a small space, maybe an inch or so in diameter. And that induces these shock waves in the air. And it's these shock waves that you hear as thunder.
It literally means that there's so much energy being released by a bolt of lightning that it creates sound out of thin air, quite literally. I mean, it's that sound that you hear as thunder is a shock wave of just air pressure being changed. And there's so much energy changing that pressure so quickly that we basically hear, this isn't exactly, but you're hearing molecules slapping together.
Yeah, well,
from
that's
like
really
miles
what sound is
away.
in general.
Right.
But thunder is just much louder than most things you hear.
And actually you can, I know that everybody's probably heard the stories of you can measure how far away the storm is by, you see the flash and then you count.
Count until you hear the thunder, because light travels at a specific speed. Sound travels at an average speed. And so you can count, and if there's 5 seconds or so between a bolt and the thunder, it means about 1 mile for each 5 seconds. And that's about 3 seconds for each kilometer.
Now, I had always heard that it was 1 second for 1 mile, so I'm glad that we cleared that up. And again, if you need the reference for that, that's in our show notes, as well as some other fascinating stuff in our show notes. And I want to touch on a few of these real quick, is that there are so many different kinds of lightning. We mentioned this very briefly at the top of the show, but there's a few specific types that I'd like to get a little bit into and talk a little bit about what exactly they are, what they do, and some of the other things about it. Let's talk about positive lightning. Now, first of all, I want to remind you guys that the typical cloud-to-ground lightning is caused by negatively charged ions in the clouds or particles pulling up and then making their way and connecting. Yeah. But there is a form that is made by positively charged particles as well. This is what they call it, positive lightning. Yes, and it's sort of, the bolt sort of goes from the cloud to the ground and then streams back up. But positive lightning sort of happens the other way. So it's the top of the cloud, actually, that has those positive charges that can come down. And they only make up about 5% of all actual lightning strikes. So it doesn't happen very often. But they're dangerous because they can travel for miles in a horizontal fashion before actually turning and reaching the ground. Oh, so it could be still sunshine where you are, and you could still get this positive bolt strike the ground. This is just more evidence that those people that go out and storm chase are just absolutely nuts. So this is okay. So again, we were talking about those cumulonimbus clouds, the kind of anvil-shaped ones. This positive lightning tends to come from the top. You're saying, and it comes from the top. It shoots off to the side and then comes down. To the side, comes back down to the ground, and then it sort of happens in the opposite direction. So most lightning, you'll see it come from the top and sort of branch down. This kind of lightning, you'll kind of see branch in the opposite direction. Oh, sort of branches coming up. People have heard, whether it comes from cloud to ground or ground to cloud. It goes both ways. It does, and technically it's the meeting of the two that causes the return stroke, that lightning bolt to actually form. It's just, But you've seen videos of very slow footage of lightning being formed, and with a typical bolt, like we were talking about earlier, you do kind of see it grow from both points, sometimes more towards one or the other. But these, you're saying that with a positive lightning stroke, you would pretty much definitely see it grow from the ground? Just because of the way that it forms? Yeah, they form in a different fashion. You can actually see they look different. They sort of look like upside down lightning bolts from what you're normally seeing. Wow, that would be crazy. Oh, yeah. Now, speaking of crazy, though, we were saying, we mentioned kind of offhandedly earlier that lightning doesn't have to come hand in hand with precipitation. It doesn't always have to be like... Now, there are forms of lightning. I just want to mention this really quickly because this sounds awesome. It can hit... lightning can strike during a snowstorm. Yes, it can. It's not very common because it usually requires warm air. Yeah, but if you have cold and colder air, it sort of does the same thing. Right. The snow can muffle the thunder, so you can't hear it as much, but there is lightning can strike in a snowstorm too. That sounds awesome. I think we have a link in our show notes to like a newscast of it happening somewhere. But the other one that I want to talk about, because it doesn't always have to follow precipitation. There can actually be lightning that hits just during heat or because of volcanoes and things like this. Does it end up happening the same way? Is it basically the same as cloud to ground? It's the same sort of idea where you're having things bump into each other. Forest fires with their ash, or sandstorms, or volcanic ash. It's all these particles mixing and hitting each other and sort of building up this static charge. So it's the same sort of idea that, things are hitting each other, electrons are jumping ship, and you have positive charges and negative charges that hit each other, and you have lightning. So it doesn't necessarily, again, it doesn't have to be rain. There doesn't have to be any water involved at all. Doesn't have to be water at all. Sandstorms, volcanoes. Sandstorms. So you could have lightning hit in the middle of the desert. Yes. That's crazy. This is all so crazy. No water required. They got to get out there and do more studying of lightning because this is awesome. But it's crazy. Before we move on, yeah, you're talking about crazy. Tell me a little bit about ball lightning. First of all, describe what is this supposed to look like? Is this literally a ball of lightning? Ball lightning is like it. Lightning is a stream. You see a little line and you draw it as a kid, and you know that that's what it is. Right. Ball lightning is more like this little ball of light that can bounce around or move. And there's not been a lot of scientific research on this because it's really hard, and a lot of it's just anecdotal research. I think they also call those UFOs, though. Just FYI, or magic. Depending on the circles that you run with. But yeah, this is why it's so weird. And we've got some explanation from some of these, but just say the names of some of these crazy theories that people have come up with to describe ball lightning.
There's the vaporized silica hypothesis, nanobattery ideas, black holes, transcranial magnetic stimulation.
Wait, what?
The last one is essentially saying it's hallucinations experienced by patients having epileptic seizures.
Awesome.
So the lightning isn't in the sky. It's in your
It's
mind.
all in your head.
It's all in your head.
No, but lightning can literally be in your head. I mean, everybody's heard stories about people being hit by lightning.
Yeah.
We've actually got a link. There's a guy in, do you guys know off the top of your head, the world record for how many times a single person has been struck by lightning? I'll give you a second to look it up. We'll come back to that in just a minute. But being hit by lightning is a common fear. I mean, that's why people go indoors when there's a lightning storm going on. That's why people take precautions all the time. Mm-hmm. But I think there are a lot of myths involved in this as well, some misconceptions. Yes. Like I actually thought it was perfectly safe to be in your car during a lightning storm.
It's mostly safe. It's, a lot of people think it's only if you have rubber tires or something, but it's not that. It's that your car is acting like a Faraday cage. There's an enclosure, formed by some sort of conducting material of mesh or wire that sort of blocks out external static fields. So that's what you're protected by. So as long as you're not touching the metal on the car, then it's probably going to follow the metal. It's going to like the metal more, and it's going to kind of wrap itself around you.
Yeah. Which, by the way, means if you're driving an old truck like I do, you're not safe at all. That thing has metal everywhere.
Or if you have an open window, because it can jump in the window.
Aha. So you do have to keep your windows closed. You probably are anyway. It's raining out, right?
Probably.
What about rubber shoes?
No, that little tiny 1 inch of rubber is not going to protect you from anything.
Yeah, I mean, if you take a look at some of the pictures, like I said, that we had in our show notes or that I've shown you during this, those streamers, those positive ions that come up from the ground.
They can form off people, too.
Yeah, and they go way past just a little bit of rubber sole. You are not protected. That's not going to protect you. And, guys, think about it. I mean, lightning does not just conduct itself along physical routes.
No.
It doesn't always hit the largest thing around. Like I was mentioning before the show that lightning has struck in Central Park despite being surrounded by Manhattan, but by skyscrapers. And these streamers come off multiple objects, and it's sort of random. Where's the lightning going to hit? Mm-hmm. So it'll probably a streamer might form off a tall object, but it'll also form off a shorter object. Now, what about if you are hit by lightning? Like, is there anything that you can do to minimize your risk? If you have to be out in a storm, like, okay, maybe some of our watchers are storm chasers. If so, I apologize for my... No, I don't. You guys are crazy. I don't apologize at all. But what can they do to minimize their risk if they're out there putting themselves in the line of fire of lightning?
If someone is actually struck, then the human skin has a high resistance, and that usually means that the lightning sort of travels over your skin and conducts along the skin. But if you're wearing anything like headphones or watches or rings, then that metal on your skin will sort of interrupt the natural flow of the lightning. It can cause burns or other injuries as well.
Now that kind of resistance, that fact that the lightning will tend to just discharge itself straight across your skin, there's a term for that, right?
Yes, flashover.
Right. And so if you're like holding a set of keys or holding on to something metallic or you have something in your pocket if it's touching, somebody in the chat room asked about fillings. I know that most fillings these days are like ceramic, right?
Yeah, and since it's not touching your skin, it might not cause as much problem. There might be a little bit of an issue there.
Would that also include jewelry, like earrings and things like that?
Yeah, anything that's metal might. So just remove what you can, anything metal that you see, put it in a pile as far away as you feel comfortable being, and then crouch down on the ground.
Leave your jewelry over here.
Yeah, you don't want to actually lay down on the ground because if a lightning strikes near you, I mean, that charge doesn't just disappear.
Right.
It sort of travels into the ground. So if you're lying flat, you can actually get more of a shock than if you just sort of crouch down on the balls of your feet.
Oh, I see. Oh, so you're saying crouch down to, again, I mean, it's not a guarantee, but if you're not the tallest thing around, there's less of a chance of you getting hit.
There's less of a chance of you getting hit. And if the lightning hits the ground nearby, then...
So if you're on the balls of your feet, you have less contact with that extra
less contact with the ground, and it'll be less charge that you sort of are exposed to.
Okay. Well, I hope that, what was the guy's name? Roy Sullivan.
Roy Sullivan.
I hope that he followed some of these tips. He's the guy that holds the world record posthumously, unfortunately, at this point. Although he did not die from being struck by lightning.
No, he did not.
No, but he was struck throughout the course of his life 7 times.
Yep. That was officially, he claims an additional one, but there was no other evidence of that. So
that is crazy. Poor guy,
yeah.
really.
Oh, yeah.
Now, we're going to have some more links just like every week to if you want to follow like probably the National Weather Service and stuff. I'll be honest, we haven't actually got them in our show notes yet. They'll be there by the time we publish though. I promise. And it probably social media, that kind of stuff. So you can talk all about lightning. I really hope that we can find some major studies out there being done specifically about lightning. Like, for example, we talked on our antimatter episode that there's a study out there regarding the antimatter that's formed by these lightning storms when they jet off into space.
Yeah, because, you see lightning coming down to ground. There's things going on above the clouds too, going into space.
Which are technically still lightning. They just are, they're slightly different in their mechanics. But things like blue jets,
or sprites, elves, various things.
Wait, elves?
Yeah.
Oh, that's an acronym, isn't it?
Yes, it is.
Oh, science. But anyway, so we'll have more information about all of that in our show notes, and I encourage you to check them out. And just as an added little bit of fun, we kind of cut some of our own anecdotes about lightning out of the technical side of this show, but I've already talked Heather into, we're going to be putting those in Jupiter Colony. So we'd love to hear about some of your personal stories. There's got some guys in the chat room that have been telling me about this. Tanner is a storm chaser. He's done lightning photography, so I hope he'll go over to Jupiter Colony, and you guys should too. Or leave a note wherever you're watching this, or you can email it.
Yep, at SciByte@JupiterBroadcasting.com.
Or you know what? If you just can't do that, if you just can't handle it and you just love Twitter, send me a note. I am JB Jeremy.
And I am JB_Marspace.
And that's all we have for this week. Now, I do want to tell you about what we're going to be talking about on next week's show. We already teased this on a previous episode, just last week, as a matter of fact, but I figured we might as well do this while it's fresh in our brains and get it out of the way. Heather, why don't you introduce what we're going to be talking about on next week's SciByte?
We're going to be taking a look at the periodic table, how to read it, what all those crazy little numbers mean, a little bit more about what it's all about.
It's much more than just pretty wallpaper, people. I mean, even the way that it's arranged. We'll get into all that. Now, it might not be the most in-depth, but we'll probably be covering some chemistry. And neither of us are chemists.
No.
So it might be interesting. I know the research will be.
Yes.
So let's look forward to that. And until then, I hope you guys have all had a wonderfully shocking experience on this week's SciByte. We'll see you next week.
There was something that you wanted me to do after the show. What was it?
Higgs!
Higgs! It's the Higgs.
So
all they've done is narrow down what weight the Higgs particles cannot be. But they are seeing particles that are very Higgs-like.
Now, what exactly do you mean by that?
They're acting enough like what they think the Higgs boson particles should act like, that it's becoming more obvious to the people who are studying it that it's got to be there. Something like it, at least, has got to be there. So they've just kind of looked in certain areas, and so they know it's not in this weight range, it's not in that weight range, so they're just kind of narrowing down where they're going to find it. But there are particles that are acting enough like it that they're getting more confident that it really exists.
That's good. I would hate for the standard model to be wrong at this point. I mean, we've been using it for like 30, 40 years for the basis of particle physics. It would really suck if it was all wrong. If they've actually uncovered the Higgs, it theoretically wouldn't be that many years before we might be able to manipulate the Higgs, right?
In theory. Seeing something and being able to manipulate it are completely different things.
I know, but
I mean, we see lightning all the time, but can we tell it where to go?
No, not yet.
Well.
But have we been able to manipulate the strong or weak nuclear forces to date?
Sure enough. I mean, there are things that we are controlling. I mean, like we control electricity to a certain degree. When you flip the switch and your light comes on.
Right.
So there are things that we can control, but
I was just theorizing that if we can actually uncover exactly what the Higgs is,
a lot closer.
I want to see. My theory for faster than light travel is someday a field that can repel Higgs bosons, so we can have a region of space free of mass.
Free of mass, then you can do whatever you want.
Relativity be damned.
Sweep
Although my brother had an interesting question, and maybe you're more sciencey and could be able to answer this. He was wondering, without mass, could you breathe? Or does that action require the displacement of mass? Because we would still have the strong and weak nuclear, theoretically, the strong and weak nuclear forces and electromagnetism, so we would still be matter. That's good. I suppose
what you'd want to do is to have the anti-Higgs stream sort of facing out of your ship. That way, you can still, you can still move like normal. You can still walk like normal.
Also, maybe more like a bubble, like a two-layered field.
Yeah, so it's just pointing out of your ship. So it creates like a little bubble around your ship.
Right. So the interior of your spaceship is still Higgsy. And then there's a region of none.
There's a region of non-Higgsy outside.
And you just move that region.
Yeah, you're just moving inside that region.
I don't know. Maybe one day.
Stuff gets crazy.
Yep.
The stuff we barely understand is crazy.
Like lightning.
Yeah.
Seriously, there's these little torch things that just generate themselves out of clouds.
Yep.
Because too much stuff got too close to one another.
Yep.
And that's lightning.
And that's lightning.
That's dumb. Okay. Well, that was fun to talk about.